All right, welcome. This is the week 2 of the R Beginners Bootcamp, and today we're going to be studying data import and manipulation. Here are kind of our learning objectives are going to be able to import, export data files, especially CSV files. And we'll look at how to handle missing data appropriately, how to manipulate data frames, kind of remember how we did it in the last lesson with base R, and kind of try to move over to using the tidyverse. Just a much more elegant way of manipulating data, much simpler and easier to use. And along with that, we'll learn how to chain operations, using the pipe operator, and a couple more things like joining data and moving around columns, things like that. This will be a very practical, fruitful exercise today, I believe. So just to get started, is load our packages. I guess the first thing we need to do is set our working directory. I'm going to be working in this R Bootcamp directory too, so we always want to set our working directory so we'll know what we're doing. I have my R markdown file here that I will be using, and little space here to I started a new file to run code as we go. You know what I mean? So first, let's just talk about working with files and directories, right? We didn't really talk about how to, and we worked with data frames last time, but we didn't really talk about how to save them or bring them in or import them and things like that, right? So let's get with that here. So, first we wanted to be able to be in the right directory. If you just look at the get working directory, if you just ran that function only, you see here I am in the folder I want because I just set it, right? So you kind of, whenever you're working in R, you want to create a directory, usually a project-specific directory, and be able to set that at the beginning of your work. And then whenever you save a file or output any kind of file, it'll automatically go, into that folder for you, and you won't get your files lost and have to hunt around for them, right? You can also run list files to see what's in the current directory, but that's more useful if you're working the command line, because we can already look over here in our directory and see everything that's, in that folder at the time. So let's just create some sample data files really quick, like we did last time. So we'll be able to pull these back up as we go in this lesson. And just creating a simple data frame here. 1 to 10 ID. I got 10 different names. Age associated with each one. These are all feature columns, if you remember. You use data.frame to set up the data frame, and then you use, remember, if you remember, each column has a feature name, and you have a vector, that's associated with it, right? Here we have, scores here. And the department they are in. We see an MA value here, which we'll be able to locate later, right? So how do we save this actual file? So there's a couple ways to do it. I think write.csv is the best R-based method to do it, base R method to do it. So here you just use write.csv, put in the name of your data frame, and then in quotes, the name you want to save it as, .csv, and you can put row names equals true or false. So what's happening here is if you have row names in your data, right, you're going to want to save row names equals true, because so what's going to happen is in an Excel file you can't name the rows, right? So if you have row names in your file in R and you save it, it'll bring that row name over to the first column. But if you don't have row names in R, right, and your columns are just named 1, 2, 3, 4, 5, 6, then you want to say false, because then you'll just have a column of 1, 2, 3, 4, 5, 6. It'll be a completely useless column, right? So basically, long story short, if you have row names, put true. If you don't, put false here, right? And here we're creating another frame. It's even more messy. It's got all sorts of jacked up problems here. We have extra spaces, Bob's different. He's lowercase. We have a negative value for age. What? This guy has 0 salary, and he's not even talking about his salary, and then we got different dates. So we're just a big messy data frame, then I'll show you how to clean up a little bit better. And I'm basically just writing this as well. I'm saving it as write.csv. And I can show you what you're going to get out of that. Let's say we want to create this file. Yeah, I did that last time too. Whenever I move my arm, I always do that, right? Okay, live data coding. You have mistakes too, right? So here's my sample data file. You pull it up just like we thought. We have our ID, which is a little bit redundant here, but so be it. Name, age, score, department, right? And let's go ahead and save this file. And you'll see here that I now have my sample data.csv file here in my directory. And we could do the same for the messy data if we wanted to here, right? I'll go ahead and do it just so we'll have it to pull up later here when I show you. So just messy data once again, writing to CSV once again, and you see it's right here, messy data. All right, so now we have our data to use later on. So how do we import that data? So let's just assume the opposite. Let's assume we had those CSV files, but how do we read them back into R if we don't have them? Well, pretty easy. There's two ways to do it. One is the tidy, one's base. In the base function, it's already built into R. It's just read.csv, right? Pretty easy. The opposite of write.csv. And read.csv, put the name you're doing there, and you'll put the path to directory. We're assuming we're in that directory because we set the working directory. And we pulled it in, looking at the head, and we see it's been pulled in. Other thing we can do, just to be a little more specific, is you want to add in strings as factors equals false, most likely. And what's basically happening there is, and let's look at department here, or even name. These names aren't factors. A factor would be, think of a factor is, we haven't covered this yet, but remember the true false logistic thing we did last time? That's basically a 2-level factor. So you could also have a 3-level factor, 4-level factor, and you don't necessarily want those specifically to be that. There's times where you would want to have that, but honestly, usually it's not. And if you don't put anything in here, like this is default false. And so you don't have to worry about it. But basically, we're keeping the strings as characters. So we want the names and the departments to be character values. And you see here when we pull in this, Alice and Bob are characters. Department's character, right? And another thing we can do is, as you notice here, we have a bunch of different kinds of NAs. NA not disclosed. You can define what an NA is in your data set by saying NA.strings, and you just make a vector here, all the different ways you could, is it just NA, is it n/A, empty? You can define these values earlier. Another thing you can do is, after you pull it in, you can just label all the values in that matrix as the way you like to have it, or you can do it in Excel before. It's just the way you either change it before. That's probably what I would do, is just change them all before. It's simpler. Or you can define them here lately. So when you call NA strings, you call NA values later, it will recognize all those as the same type of value. But anyway, here's our matrix here, just as above, and we see here, our data frame, and we pull up the structure of it. We see our different, feature columns and what they are. These are integer values, same as numeric, basically, and we have our character values too. Alternatively, we can use the tidyverse, we haven't gone into yet, but the tidyverse is just a set of functions I'll talk about in a minute that just handles R just a more elegant, easier way. And what you can do is you can use the reader package, which is in tidyverse if you load tidyverse, and that is able to read the CSV in the same way. Instead of .csv, you put a lower slash there. And what that does is it'll figure these things out for itself. It'll figure out probably that you don't want the strings as a factor, and it would have found all of these different A values and put them all together. And basically it makes a tibble, and if you look at that, Tibble's the same thing. It's a tidy version of a data frame, and you see here are all our feature vectors laid out the same way as we would see them up here. You see this double here. Double just means numeric, actually, a double precision vector. It just goes from a long way of the way things used to be. Integers coded as 32-bit. A data frame or a tibble could be coded to 64-bit. So it's just saying double precision vector. But when you see double, just think of numeric or integer value, right? It's just an easier way of doing it. And the cheat way of all this, as I said all this, the cheat way to pull in a value is just, let's say, go in here in our directory and just click on sample data and import data set. And you see here on the bottom, it's doing exactly that. It's saying library reader, and it's running that code, exactly for you. So that's kind of the cheat way, but always best to hard code things. So when you pass on the data or you change the files, it does a lot better. So that's how we save a file and we pull that back in to R to use. Simple but important. Reading Excel files, you can use the package I put in earlier. I forget what the name of it was. It was the read x1. And basically you can able to have a bottom score read Excel, your file, or a certain sheet or or range. I would never do this though. Excel files are a big mess. The only reason you ever use an Excel file basically is to add like a chart or colors, things like that. So always just save your files to CSV files and load them in as your data frames, and it'll just make your life a lot simpler. Another way to write things. What if you wanted to write? If you wanted to write a table, well, write that table. I can put all my table. I can use my same sample file and write it to a text file, and use basically a tab separated. So CSV means comma separated value. It's just the way the different lines that are coded in the deeper programming, kind of each line, what is used to denote a line, you know. And a text, it's normally a tab. It could be other things like a semicolon here, pipe, things like that. But long story short, if you want to write a table or anything else, you can put the way you want to separate it, right? And the same thing, you know, row names, as we talked about above. If you want to read that back in, you do read.table. And your sample header equals true just means you want to set whatever the column names are here as your column names and not just as the first row. And if you said false, it would just be the first row. ID name, such would be the first row. Header equals true, they're actual column names. And the separation, whatever the separation was, you pull it back in. So that's how you handle different, you know, delimiters going in and out. And as we mentioned earlier, when we started out at the very beginning, creating our files, you know, write to CSV, we figured that out. The quotes, it's the same thing. We don't want quotes around the strings if we put them out. This is usually going to be default equals false. So rare that you'd ever want to have the quotes on there, right? And same thing with these guys. We just looked at this, the right table. And you can also, you know, remember if you use the tidyverse way, it'll be the right underscore CSV as opposed to dot to get out, right? All right, so now we know how to pull in data, write data, go back and forth. Good job. We're handling that right. The very beginner things that'll cause you a lot of problems. You don't know them. Okay, so one of the things we deal with a lot in R or any kind of data science is missing data, right? So that's one of your biggest problems that can confound your entire analysis. So how do you handle this missing data? So let's look at some of the just very beginning ways of looking into this. And then later on, you'll have more advanced packages to handle this as well. So let's read our sample data file back in. You know, we already have it anyway, right? This time we're going to name it data frame within A, just to get it out, to separate it, and we'll look at a summary of this. And remember, the summary just kind of gives us an idea of each, you know, it'll give us a distribution of statistics per feature that's numeric, and it's kind of trivial a little bit if it's character. But anyway, the important thing is you see NA is equals 1. And score, remember that score had an NA. So there's our problem there we have to think about. We can also say, like, how many NAs are there in each column? So we can do this, we can use column sums. You can column sums anything, and it'll tell you how much of anything is in each column. Well, what do we want? We want to know, is an A? Is there an NA in this data set in each column, right? And it's just going to give us, every time it's yes, it will add up a value. So we have that 1 underscore here. What if we just wanted to find the rows they were in, right? Well, if we did that, we'd use complete cases. So basically, complete cases is like, is there a complete row in this data frame? Well, if it's complete, then that means there's no NA, right? So we want the NAs, right? So we use remember the exclamation means not. So we want all the not complete cases. So every row that's not complete, every row that has an NA. So we're picking out the rows. Remember the brackets here are our subsetting, and we have the comma here, rows, column. So we want all the columns, but just the rows with the NA. So bam, there you go. We just have the one with score NA. We're doing great, right? What if we want to get rid of those rows? We just want to get rid of all the rows with the NA. You have to be very careful with this. Let's say you have a RNA-seq data. Well, there's a lot of NAs in there, or they can be defined as 0, or it's confusing if they're NA or 0, right? But if they're in, you can't just throw out half your data, right, with this function. So be very careful. In this instance, it kind of makes sense, but just be very aware of what rows you want to filter. Do you really want to filter them all? So if you want to do everything, it gets rid of every single row with an NA value, use the NA.amend function here. You can see if we look at the number of rows, now there's 9 because there was originally 10 and 1 has been removed. Let's say we want to replace an NA, and this is really important for imputing data. A lot of times there'll be just a couple values that we're able to impute. Now this is very controversial in genomic data. Is it okay to be able to, it can be difficult to figure out the ways where you want to replace NA values or not in that data. So this is a good example of a good time to replace it. Remember, it's Frank, right? So Frank here is hanging out here. He has an NA value right there. So how would we replace that value with a logical number and to be able to run? A lot of times you need to have a full data set or you can't run your upcoming analysis. So let's think about how we could do it. Well, one way we could do it is just replace that value with the mean of that column. So if you look at all the data, the mean would probably represent the closest, or median. We'll do mean in this case. It gives you a good approximation of what the value could be. So let's do that here. So let's just make a matrix called data frame filled. And what we're basically looking at here, we want to look in the data frame filled score column, right? And we want to look at every row that has an NA, which just happens to be this one, right? Or really every value, because this is not a row, this is a vector here, right? This is just a vector. So that's why there's no comma here. So we want all the NA values. There just happens to be one, so we could have just subset it. But we want to look at this, future-proof this code, where it's going to replace every NA with something over here, right? So let's find the mean of that column, right? So we want the mean of the column. We want to remove all the NA values in that calculation, not in the data set. So in this calculation, NA.remove equals true, removes that NA. So we just have all the rest of the values. So it would throw off the mean, you know? So that allows us to calculate the mean for this vector and replace all NA values with that number. It just happens to be 1 in this case. But so the mean of this column is 87.77, and it's been replaced here. So this is really good. There's times where I've done this in data sets and replaced things in the mean too. So it's the average does make sense in a lot of instances. Okay, well, going forward, so let's say, just kind of remind you of kind of some of the base R manipulation. So when we go forward to the tidyverse, you'll remember what we did last time. If I remember last time, it's just subsetting. If you wanted to, we would put our data frame in our brackets, remember? And we'd have a row, comma, column. Row, comma, column. So here, there's nothing there in the rows. So we want all the rows, but we just want the names of these 3 columns here. So it's basically getting all the rows, and then it's grabbing whatever you put here, name, age, score, right? We could have also put 1, 2, 3, right? Or 1:3. We're just subsetting, making a vector here. So we have the C that combines all these together to get this subset, right? As you saw here, we could have also done the comma, a vector 1, 2, 4. That will grab us the ID, name, and score. Very similar, we're using numbers instead of that. Then we can, remember we can filter by a certain kind of annotation, like we want all of the data frame ages less than 30, just those rows in all the columns here, right? Or you can do even more complex things where you look at, I want all the rows where the department equals IT and the score is over 85. So we're grabbing those 2 conditions basically to grab those rows. And we can also, do a complicated subset function here where it's basically looking in, is the department in those 2 things? So you would, if it's in that or that and over 30, you would grab it, right? Important things is just all remembering the way we did this in base R. Creating a new columns, if you remember, we just basically just do the $sign and add something like this bonus, just adds this column, and here we're just multiplying the score column by 10 to get this column. The important thing is how you add a new column. You can add a new column based on a condition, or you can also modify an existing column. You guys can check that out on your own, but it's pretty simple. And removing columns, you could say I want to remove everything that's not associated with bonus and performance, for example. But it'd be easier, I think, this is kind of the most complex way I wanted to show you. But if you remember also, we could just do the negative, like negative age, comma, negative score. It would get rid of those 2 columns. But I just want to kind of remind, this is all just to kind of remind you of the lesson last week of how to subset these things in base R. So when we move the tidyverse, you'll see the difference. So tidyverse, what is tidyverse? Well, good question. Let's go and look at tidyverse, right? Should have had this open earlier. Tidyverse is a really cool, just universe basically. It started by Hadley Wickham and some other collaborators, and over the last decade, they've built all of these packages that basically make things easier for you in R. You know, you guys know ggplot2. People use it all the time, and you know, diplar we're going to talk about just in a second. Things like reader we use to read in, and things like tidyr, per. We use tibble member for matrix. There's all sorts of different packages. They're not all here. This is just the core tidyverse. But it gives you a more everything's are named better and simpler, and just makes your life a lot easier. I think I would start moving toward using this as opposed to the base. But it's your opinion. You can do one or the other. So the first thing I want to talk about is the pipe operator. First thing I want to introduce. So the pipe operator is what it really thinks like. It's just a pipe, and you see it's going in that direction. You're just piping one thing to the next to get one thing done after the next. And here's where you can see kind of how this can look more elegant. Here is a kind of the nested approach that you'd normally use in base R. So you see here, I'm choosing the data frame, the age column, and I'm sorting it, right? And then after that, after I sort it, I'm doing the head of the first top 3 values. So I'm getting a sorted of the sorted numbers of that column, right? Well, usually a better, more elegant way is to use the pipe. So we have our result, right? So what you do this in tidyverse, you put your object up here, you do your arrow, and then after that, you do what you're starting out with, what vector or data frame you're starting out with in your pipe object, and then below, you do a tab or 2 spaces for each line that you are going to do an additional function. And then you just do a pipe each time you go down. So here we're starting just like this. We're doing the age, then the sort, then the head, right? Well, same thing. We're doing the age, we're finding the vector, and then we're piping it to the next function. Then we're sorting it, just like here, piping to the next function, and then we're doing the head 3, just like we did up here. But if you can see, it's much more elegant than this kind of nested approach. You can especially imagine there's like 15 different lines here. You wouldn't want to look at some super complicated nested function. This becomes a lot easier to see and read. You get the same result here. So if you just wanted to do, one operation here, you would just you could do data frame, and you don't have to give it to a new result. If you just want to basically just print something out, you can just do your data frame pipe number of rows, right? It would just give you the number of rows, 10, right? It didn't assign it to a new value like I did here. So you don't have to have the arrow if you don't want to assign it, if you just want to see the result. Just like the summary here, we just want to look at it. We don't want to define it. So we don't need that extra arrow. We have our data frame, pipe, and then our summary, just like we saw above. So what are some ways we can use diplar further in order to be able to manipulate and arrange these data frames, right? So if you remember, before to choose columns, we had the brackets and the row dot column thing, right? Well, here's a little bit easier, more elegant way of doing it. Let's use select. This is the first diplar verb we're going to talk about. So we have our data frame, we have our pipe, and we're doing one function here. We want to select the columns. So we select the name, we put the names of the column. We don't even need to worry about the quotes or anything. It's just so much easier to use, right? Name, age, score. We could have also put the numbers here, 1, 2, 4, whatever they were. You could do either way, and we'll be able to select these columns. You can do fancy stuff like this. I want to select columns that start with A. All right, so that gives us a little bit easier group, or you could say it starts with the first 3 letters, things like that. That's very useful in genomics, MRNs, things like that. So that's the way you can select. So really, you're just select, and then whatever the columns you need. If you want to do the opposite, it's kind of like before, you do a negative. So I want everything but bonus and performance. That's what I got here. And if I want to reorder columns, then whatever order I put these in, they come. If I would have said age, name, score, you would have saw age come up first. So it's an easy way to order them at the very beginning. And you can sort the whole thing. You can sort select, or you can just put them the way you want, right? And here, everything refers to everything left. So here I'm putting ID, name, department, and then everything after that. I could have put any other way. It would any way I want it, it can come out. That's the point, right? So select is how you choose your columns. Now filter, in contrast, is how we choose our rows. Select columns, filter the rows. It kind of makes sense. We're selecting features and then we're filtering the observations that are associated with those features, right? And so here we do filter, right? And for instance, we could filter out all the rows where age is greater than 30. So that's what we saw here. We can do multiple things like an and. So a comma is an and. So we want to filter age is greater than 30 and it's equal, department is equal to, double equal signs, the IT, right? So we have everything, these ages are over 30 and the department. Or you can do an or condition, or you have this kind of, this vertical line here, and you're saying, I want things that have age over 35 or the score is over 90. So you'll get one or the other. And then if you want to see something that's just in something, I want to choose filter all the departments that's in sales and ALR, right? So I'm just choosing the departments that are in sales and ER. You could have done an equal sign twice, but it's just kind of easier to say the in. And finally, filtering out ends is really easy. So I want to filter rows. So remember, I can choose the is and a. So I want to choose the NA values and score. And then we have the not exclamation, right? So I want to filter rows that don't have an NA and score, right? So I want the rows that don't have an NA, right? So if they had an NA, they would not have been selected. All right, so there we go. We've selected our columns and we've filtered our rows, right? So how do we create a new column? Well, now we have mutate, which is kind of a cool name. Mutate, change, I guess, right? And instead of having just the names and an equal sign, now we'll use mutate for each column we add, right? So data frame, mutate, add a new column called score doubled, and then any kind of vector that would be able to associate with that column. You could have put anything here. Here we just multiplied the score column by 2. But it could have been anything, and that's how you add a column. Well, how would you name multiple columns? Well, mutate, just put several different things. It's very similar to what we saw in the data frame, right? I want to add a score doubled equals this. I want to add is senior. It's going to have a condition where the age is greater than 35. And then I want to add a column that also, where the name length is a character name. What's the length? You know, how many characters are in a name, basically. And so I've created these extra columns, and then I'm kind of looking at the head of it, right? And if I want to modify an existing column, right? We saw above how to do that. Now we just go age equals age plus whatever. So we just basically just use the same name and then use your modification. What about complex conditions? The same as before. We can do, say we want a new thing called category, right? And then we do a case when here for complex. So for each one of these, it's going to give a certain element or answer based on this case when. So if it's greater than 90, you'll get A. If it's greater than or equal to 70, you'll get a C. Otherwise, it's a D. Add those. This is kind of a conditional, complex way of doing it. But the important thing is mutate and whatever your feature name is and equals to your vector adds a column. So now we've selected columns, filtered rows, and then add columns, we use mutate. Okay, to sort, we use a name called, instead of sort, we use a range here. So here we use a range, age. It's going to go from low to high. If you want to do it the opposite way, you would do descending. So instead of ascending, you would do descending. Same thing with the score, right? It's going down. And A's are always put at the bottom. If you want to sort multiple columns, you could just do a comma. So I want to arrange department, right? And then within each department, I want to have a descending score. So you see within IT, it's going down, right? And sales is going down. So you're doing 2 columns. And then to summarize, kind of like summary before, you just do summarize. Summarize, and you just name which columns you want. So here I'm just summarizing the age only, and I'm saying I want a column named mean age, which is the mean of the age. If you want to do multiple ones, here I'm summarizing the mean column and the score column, and I'm counting and I'm doing departments. So I'm making a new column named mean age, and I'm saying mean age. I'm making a new column named max score, and I'm basically saying the max of score if you don't count any of the NAs. And then I'm saying the number of people total, and I'm using equals, and it's just going to always give you the number of observations. And for departments, I'm saying how many distinct departments are there, not how many total, right? And I'm getting a 4 here, which makes sense. There's 4 columns. There's 4 different departments. If you want to filter and then summarize, well, I want to filter out everything to do with IT, pipe it to summarize. So these values are just associated with IT to begin with. All right, so let's look at the big one. I think is the group by. So group by, you just want to pull things together in your matrix. So I want to group by department. So that would give me a column department and just have everything going there, and then I would summarize basically anything else I mean. So it would just have everything grouped, and then here, I want to summarize the count, the mean age, and the mean score here. So I'm just adding these columns to what we've summarized here. I could also do something more complicated where I just group by department again, and then I add 2 different columns, department mean score, and score difference based on other columns. And then finally, once I have that, I just want to select out these guys in order. So it's just a more fancy way. The important thing is to be able to group these items together. If you want to group multiple variables, like you want to group by department and age group, you will see here that it will put out all the departments together, but then each one that has multiple age groups, instead of having one IT, which you'd expect by group by, you would have the age groups in there too, because you've added that. And then once again, we can summarize by anything we want to add as a column and condition. And you can obviously put all this together. You can combine a lot of these together. We're filtering out everything that's not an NA and score, and then we're adding a new category, score category that has different annotations for score. Then we're grouping by department, and then we're summarizing that, and then we're arranging it basically. So we basically got this group by with these new score categories we've added with the accounts and mean age associated with that. This is kind of a fancy way. I know it's a lot to throw at you, but you can kind of look through this and kind of get an idea of how to do that. Another thing you can do here, same kind of thing here. You could, you could filter out, group, and one thing you can do is slice. Slice max is another function we haven't talked about, but if you slice, it's just giving you the top values basically. If you were to put 2, it's giving you the 2 top values. Just more ways of kind of getting things together. So let's look at an example of data cleaning in this context. So the whole point of this is data cleaning, right? So remember that messy data we made that really messed up? It had the wrong dates, the wrong everything, right? It was just really messed up matrix. So when we print that out, you can see it's a big mess. Alice these have weird spaces. Bob's not capitalized. He's all capitalized. There's not even a value for this name. We have a negative age, no salary. What's going on? So how we can't work with this, right? We got to be able to fix this to get it together into a nice cleaned data. So let's just go line by line and figure out how we could do this. And this is most of the stuff we've shown, but some extra little functions too you can see. This is just an example of a really bad case and why and how you would clean these things up. So we start off with our messy data frame, and we pipe that to clean names. The first thing we want to do is we want all the names to be when we have the names always pulls the column names, right? So if you rename, it's renaming column names. So rename all to lower. That's making everything on the top lowercase. As you see down here, now we have everything lowercase. So you always want lowercase in the columns. And on the observations, we always want the first letter to be capitalized, unless it's a gene name, something like that. Unless it's specific, but generally we want a capitalized first letter and a nice lowercase after that, right? So let's look at the name column. Now the name has been changed to lowercase, right? So we name, so string trim name, that gets rid of the space that was around Alice. String to title name makes it a title. So you have, uppercase A to start with, then lowercase after that, right? For each name. So we've taken away the white space. We've made a title a proper case, right? Now we want to get rid of these ages. The -5 makes no sense, right? So we're basically saying if age is less than 0, or age is greater than 0, greater than 100, then put it in a value. Otherwise, do age. So in this instance, nothing, we have basically age is less than 0 for Charlie. So we add Charlie an A. And then age is greater than 100, we'd add an NA value for age there as well. And then we also want to remove all here in salary. We want to get rid of these commas. So remove all, string remove all, salary, comma. This comma is now gone. And then we want to make salary all as numeric, if it wasn't already, just to make sure. And then we want to filter out everything in names that doesn't have an NA. We want to choose everything that doesn't have an NA. So any NA value we don't want. So you can see here, we lost the column 5 because it does not have, it has an NA for the name column here, right? And then finally, there's a function, I think I put it in earlier, looper date, and it makes handling dates really, really good. And basically, you can just put this function YMD, year, month, date, and you put in your function, and it basically, you see here, they're all the same except this one has slashes. If I put YMD start date, it's going to fix that value and make them all the same. So what we're left with is all lowercase feature names. We've everything. There's no spacing with Alice, and everything has a capital to start with, lowercase, proper case. We've gotten rid of the bad ages. We put an NA for that. We've gotten rid of, we've kept, our salary NA. That makes sense. We've gotten rid of the comma and made them all numeric. And we've gotten rid of the value that has no name. So now we have a really good data set that's really nice and clean to work with. And if you want to do NA.admit, we can even get rid of both these columns as well. But we have so much little data, we probably want to keep them. We could do the mean and replace here, or both of them, or we could keep them as they are. So let's just go through a couple of practice exercises now where we do this, right? So let's first make a data set, just random data set about products 1 through 8, our product names here, our prices, our categories, and we're saying, like, is this in stock or is it not? And this is really simple. We just want to read this. Let's just want to send it out, bring it back in, do a couple calculations here, right? So simple. We make our matrix. And once we have the products matrix, we do, remember, write.csv, products.csv, and row names equals false. And then once we have that, we want to read it back, right? Well, read.csv, products, brings it back in. And then once we have that, we want to filter, what did it ask for? For products under $100, right? Well, let's look at price, right? So that's products, let's see, products, filter, want to choose rows where price, which is a feature, is under 100. So you just run that and knock it right back. And then I want an average price by category. Well, by category, that already tells me we want to group by category, right? So by category, group by category. So we do our matrix, we group by category, and then we just summarize average price. Remember, we want to average, because we're doing our summary, we add an average price column, and we do the mean of price, because we want the average price by categories. Now we have the average price by each of our different categories. So that wasn't too bad, right? So number 2, we're going to make a complex diplar pipeline. So for the same thing, we're just do some kind of groups and just try to, same matrix, let's just do a little more manipulation, baby. So here, we're going to put our products, and we want to filter for in-stock items only. So in-stock equals true. And then we'll want to add a column called price range. Case when price is, if it's less than 100, it equals low. If it's greater than 300, if it's less than, okay, so if it's between 100 and 300, okay, well then price is less than or equal to 300. Because we know if it's less than 100, it's low, right? So if it's less than or equal to 300, so that's 100 to 300, it'll be medium. If not, otherwise equals true. So that'll give us our price range here. So we've filtered just items that are in stock, and then we've put in a new column for price range, and then we want to group by our category because we want to remember price range by category. Whenever you see by category, you want to put a group by, right? So group by category and price range, right? So you want to know the category and a price range. So group by the category and the price range, and summarize the counts, count items, and then arrange by category, descending count. So now we have our categories, our different price range, and our conditions, our counts, and arranged in the proper way that we wanted to do it, right? So let's do one more. This is data cleaning, a big mess. Let's see if we can fix this big messy sales, a new messy sales here. So I already see problems here with these slashes, this NA value, white space over keyboard, headphones isn't capitalized. We have a dot here and a comma here, an error, and a negative quantity. So let's just try to see if we can fix all this up for us, right? So we have our matrix here. Let's try to clean this thing up. So let's kind of go back to the things we've looked at. So date, we want to, change the column, mutate, we can adjust the columns, right? So we date equals date will give us a new date, right? So date equals string trim member, that gets rid of the white space, and then the YMD, that fixes the date. So now we're good, our date's fixed. Product range, what are our problems? Spaces, so string to trim, and then our title issue, our case, right? String to title, so that fixes product names. The amounts, we want to get rid of that string remove that comma there, and then we want to make everything in that column numeric. And then we want to fix quantities that are negative or below zero, right? They don't make sense. So we look at quantities, we have this negative value. So we say if quantity is less than or equal to 0, put in A. Otherwise, just put what it is. So it just basically gets rid of that -5 should have an NA value, right? And let's filter the dates, right? Filter the rows where there is not an NA. So I want rows that don't have, so I'm filtering out the row that has this NA. And then look what I get. Everything looks pretty freaking good, right? Let's see. The messy sales. And we get our, everything's fixed here. I put the wrong, I called messy sales here instead of clean sales. Let's do it. Let's do it ourselves and see what it looks like, since I called the wrong data. Of course, if I call the wrong data, it's not going to look good, right? So messy data, we see all of our big, let's see, messy sales, right? Messy sales. All right, we see all of our values here that we have problems with. And then let's put in our new, we will do our, let's do our new function that we've been working on. And I will run that. And could not find function. That's because I haven't loaded the tidyverse, right? All right, so that gives us a little better. And now we can run this. And let's look at clean sales now. Okay, here we go. And let's see. So we've gotten rid of, so you can see our data's all looking pretty good. Our problem is more that, our dates are fixed now. Our product names are fixed. Our amounts are fixed, but we still have NAs in the quantity columns. But because the quantities were -5 and 0, because I said if it's equal to 0. So we got a 0, an NA there, and a negative there. So we only filtered rows that are in date. So that's why we're left with NA values and quantity, and we've taken the ones out with date. But as you can see, everything else is clean the way we want it. All right, so we did a good job on that. I need to think about, oh, here we go. I'm an idiot. I gave the first messy one and then I did the clean one, but we got to work it together, so we got to see how to do it. So here's our answer here. All right, so next I want to talk about joining data. So this is extremely important. We touched on this last time with the merge function, and we had like our data frame and some columns matched. We tried to merge on columns. So that's the way that you would do it in base R. Let's see how we could do it in tidyverse. So first, I made these two tibbles, which is a data frame, or tibbles tidy for data frame, and they're just kind of have a x value, y values. So it's basically a vector of x values, a vector of y values. X is just ABC, Y is BCD, capital, right? So there's three ways to join in tidy: left join, inner join, full join. Left join is going to keep everything on the left side. So left join X. So everything in X is ABC, right? ABC. And then I want to left join everything in Y by the ID. Okay? So if you look here, ID is 1, 2, 3 for X and 2, 3, 4 for Y. So which ones match between the two? 2, 3, right? So I can only join the Y values that match. I don't have a 4 to match. So I have all the X values, A, B, C, except the left side. And if I switch these, I would keep all the Y's. But here we have X on the left. So I keep all the X values here, and I'm matching the Y's that can be matched. So I can only match the IDs 2 and 3, which are here. 2 is B, 3 is C. So B, C, right? I put an NA there because there's nothing to match. I don't have a 1 to match. So that's how we do left join. And that's the way to preserve all of the left side of values and just merge things that match. This is probably the most useful, I would say, too. If you have like huge thousands of columns of gene names, you want to match some, things like that. Like you bring on a new attribute or a new feature. Okay, so for inner join, you choose only the things that match. So so only the things in X and Y by ID that match. Well, which IDs match, right? 2, 3, right? So we can only keep 2, 3 in each of them. So we keep BC 2 and 3, BC 2 and 3. So left join, remember, we keep the left, match only the things we can from the other side, from Y. For inner join, we just keep what's available, what matches in each of them, right? So you may guess full join is you keep all the data. So for X, I have to keep 1, 2, 3. So X, 1, 2, 3, ABC. For Y, I keep 2, 3, 4. So I have 2, 3, 4. But I need all the data, right? So I have to have 1 through 4. I have to have all the IDs. So 1, 2, 3, 4. So in this case, for 4, I have an NA value for X, and for Y, I have NA value for 1. We've kept all the data. So left join, keep the left, bring on the right. Inner join, left and right have to match. Full join, you want to bring in and keep all of your data. And if you look at another example of this, if you look at data frame here, below that I've made here, and if you want to do an inner join, you'd want to keep inner join by department ID. You'd want to keep all your department IDs, which are 1, 2, 3, 1, 2, 3. What employees departments, right? So employees departments. You basically don't keep. Let's see. Oh, I'm sorry. You keep everything on the right. So you want to keep all the employees and then just match the department IDs. Oh, sorry. Inner joins. Inner join. We keep only things that are. Oh, I keep looking at employee IDs. So yeah, by department ID, right? So you want to keep department ID. And you want to keep employees, departments. Okay, so you want to keep, sorry, I'm gonna confuse myself. But you can see it's not always simple, right? So you want to keep all the department IDs on the left, right? So you want to keep all of 1, 2, 3s. So you have 1, 2, 3s only. I kept wondering, where the hell is that for? So you have all the department IDs because you want to keep that, right? And then you want to interjoin just the departments, right? So you keep all, it's kind of like before, but it's the tidy version of this. So instead of XY, we're doing employees departments, right? So employees, and then bring in the departments on the right. And it's just piped, right? So we have employees, keep everything in the ID, and then we match the ones that can match. So we can only match the departments of 1, 2, 3. We can't match the 4, right? That's why we don't see finance in the department name. And if you want to do left join, so these are the only ones that match. If you want to do left join, it would be the same thing actually, because you would bring in, sorry, the inner join is everything that matches, right? So just 1, 2, 3s. Left join is you take the left, right? So inner join, once again, it's keeping everything that matches, which are these. Left join, it brings everything on the left and matches, so you don't have the 4. And if you have a full join, you want all the data. So you would see, all the data in there, and you would have, for things that didn't match, like here. See, this we're doing it for employee ID this time. So we bring in all the employee IDs, and we bring in all the data, and some don't match. They become NA values. And the same thing, we can do multiple joins here, where we left join by departments and department IDs, then we left join by products. You can kind of go through it yourself to kind of see how it is. If you get confused, like I just did, go back to this joining example, and you'll be able to figure it out from there. So, sorry about that, but I think it makes pretty much sense. Finally, I wanted to show you this row names from columns. So this is really important if we want to move basically columns to row names. So if we have, you can see here on the bottom here, our first column is our name. We want to build, how do we move that over to rows? Well, column name, over to row names. So we have our data frame, and then we say a variable's name, and we say column to row names. It moves the name over, as you see here, to the row names. Now our row names are this. Let's say we want to move the row names back. And this happens all the time where you have genomic data or any kind of input data where you want to basically put it in to an advanced package in R. It's always, a lot of times it's going to want the row names, the observations as row names, and not the row names as 1, 2, 3, or whatever that is, right? So in that case, you would you want to move them kind of back and forth. So here you see I say the name, and I want it row names to columns. Row names here have gone back to the first column here. So that's how you move them kind of back to forth there. Kind of just some tips and best practices to follow. Common fit points to avoid. Do your and name equals true or false if you want to remove those when you're calculating statistics. So you don't want them to have an extra value to divide by or whatever. Always check your structure, and base R or glimpse would be the term, and tidyverse. As you go along, change the names so you keep your don't ever write over your first initial count matrix. You want to be able to have a copy of that raw data. You don't want to overwrite that as you go. So rename it when you start off. Remember, the strings as factors equals false, which is default. To bring in the strings as character vectors, and make sure your packages are loaded, right? A couple of other things, some useful shortcuts that we had talked about. You can use distinct, which is basically unique. You can do count right away to give you the number. You can slice, basically, instead of doing like a head, you can slice 5 or however many random rows. You can remove duplicate rows with distinct as well. And you can rename columns easily by using the rename functions. Rename whatever column and change the name to it. And a couple other things I want to show you. There's a diplar cheat sheet. If you remember, it was back in, I showed you last time. If you can go get the different kind of cheat sheets, this will basically go over a lot of the things that we talked about today and in the diplar world. And here, sorry. And you can also, go to that R for data science book, data import cheat sheet, and things like that. But I guess this is it for our week 2 session. I hope you guys enjoyed, where we covered more data point import manipulation. Please work back through, look at the practice exercises, look at your additional assignment, try to work through it yourself if you can. Always look at the answers if you can't, no problem, and just try to kind of work along. Programming is just trying and working along with it, and just try to get a little practice for that. And we will see you next week, where we'll cover more ggplot2 and other associated data analysis. And I'll see you there. Thank you.